Give me a second.
Yeah. Yeah, now Siddhi, take over.
Okay, so welcome everybody to today's session of this lecture series at Bhaskaracharya Pratishthan, Pune. We thank Professor Winnie for the wonderful first talk, and today she will be continuing.
Siddhi, take over.
Okay, so welcome everybody. Sorry about that echo. So as I said, today we have Professor Winnie continuing the discussion on modular forms. We have modular forms too. Professor Winnie, you can start.
Thank you very much for the introduction. So let me continue. So I will start with where I stopped last time. So we have a normalized new form of weight k, level k, and a character chi. And we associated the L functions, which is a Dirichlet series with the coefficients an coming from the Fourier coefficients of G. Then we talked about the analytic properties of this associated L function. And this property put together, we call that AG. Okay, so the first is that the LG can be continued to the whole plane, and which is holomorphic everywhere, and it is bounded into vertical strip with finite width and satisfied functional equation. And for that, we multiply the gamma factor, which has a type 2 pi to the minus s times gamma s. So after we do that, then that's a functional equation relating G with the complex conjugate of G and the S, and then the weight k minus s, okay? And then in front of that, we have the exponential function part is the level to the k over 2 minus s, and there's a non-zero constant in front, okay? So, so I'm just going to call this condition A of G, okay, without repeating it each time. So today, the first question we will be talking about is the so-called converse theorem. So namely, if we are given a sequence of numbers with the polynomial growth, and that we define a function using this an as a Fourier coefficients, so series an q to the n, and that gives us a holomorphic function on the upper half plane. And the question is that when is this F a cusp form for some congruent subgroup? Okay, so any answer to this question is called a converse theorem. Okay, so this was first initiated by Hecke. He asked when an F is some cusp form for SL2Z of weight k, and his answer is in terms of the analytic behavior of the associated L function. So just of the type that I just described. And he only needed one functional equation, okay? And that's because the functional equation is the Manning transform of the fact that F stroke the inversion is equal to F, okay? And then they, in 1967, extended this to cusp forms of weight k for the group gamma naught n. Okay, so when this n is not 1, and usually one functional equation for this L series is not enough. So he also considered L series attached to the twist of F by characters. And these are the Dirichlet characters with a prime conductor and with a co-prime to n. Okay. So then I extended Bayes' converse theorem to apply it to a cusp form of weight k, level n, and a character chi. Okay. And so as we can see that for when we go from the SL2Z to gamma naught n, all of a sudden we use a lot of the twists. Okay, So later I proved that if the L function has Euler product, we actually only need a twist by characters with conductor dividing the level n. So then when n is equal to 1, it goes back to the Hecke theorem. Okay. So let me describe Weis theorem. So first, let me explain this twist. Okay. So, so the first is when you have a modular form, you twist by a character. That means that you change the Fourier coefficients by multiplying it by the character, the value at integer n. Okay. So if I start with f with which is new form of a level n character chi, and if the conductor of the character eta is co-prime to n, then the twist is again a new form of the same weight, and the level will be the n times the conductor squared, and the character will be chi times eta squared. Okay. And moreover, for this new form of tensor eta, in this functional equation, that constant is related to the constant for f in a very explicit way. So namely, the quotient is the Gauss sum of eta over Gauss sum of eta squared times eta at minus n times chi of m. So it's very, very explicit. Okay, that's the advantage of twisting by character with conductor co-prime to n. Okay, so Weis counter theorem says that so if we start with f, as I said at the beginning, okay, now if the L function has the analytic behavior as I described in the three conditions, and the same for the twist by characters, eta with prime conductor co-prime to n. Okay, and moreover, the constant associated to f twist by eta and the constant associated to f, they are related by these explicit relations. Okay, if that's the situation, then we can conclude that the f is a weight k cusp form for gamma naught n. Okay. So I will talk about the three important consequences of the Weis converse theorem. Okay. So the first, let's take Hecke-Grossen character of a ray class group of an imaginary quadratic extension K of Q. Okay. So this chi is defined on the, you can think of that defined on the integral prime ideals, and which should take value 1 on the principal ideal, which has a generator, say, congruent to some count to 1 modulo some prescribed integral ideal, and also maybe some positivity conditions at the real embedding. Oh no, this is imaginary, so that there isn't that. Okay. And you can also think about chi as the ideal class character. Okay. Okay. And we say that chi is algebraic of type K. So there's a condition of chi at the Archimedean component of the ideals, so which is a C cross. Okay, so we take a non-zero complex number. Okay, we write it as the its distance to the origin times the unit vector, and so then the chi will map such a complex number to e to the I n theta. So it just take the unit vector raised to the nth power. So here n is a plus or minus of k minus 1. Okay. So if the character chi is not regular, that means that it comes from a character c of q, then composed with a norm from k to q. So in this case, the L function associated to chi decomposes as a product of the L functions of characters of a Q. One is associated to C, the other one is C times a quadratic character associated to the extension K over Q. Okay. So in this case, this is the L function of an Eisenstein series, and we are not interested. So we assume that chi is regular. Okay. So in this case, Hecke showed that I take this L function associated to chi. Okay. So I just shift the variable a little bit by changing it to S minus K minus 1 over 2 to get a Dirichlet series. And then this L function will satisfy the conditions I listed at the beginning. And with the gamma factor, which is what we like, is 2 pi to the minus s times gamma s. And the functional equation will be relating the chi to chi bar and s to k minus s. Okay. And the exponential function in front of it is the absolute value of the discriminant of the field times normal of the conductor raised to k over 2 minus s and times some non-zero constant. Okay. So similarly, we can twist this chi by a character eta coming from Q. Okay. And then we'll find out that the constant C attached to chi tensor eta and C chi will relate the way we want it, so that everything holds, and we can apply that. We can, if we form a function whose Fourier coefficients an comes from this an of Dirichlet series attached to chi as we set up at the beginning. And then this f chi is the cusp form, which is a new form where k level is given by the exponential function here. It's a absolute value discriminant times norm of the conductor. And we also know its character. Its character is the chi itself restricted to Q, then times the quadratic twist. So everything is very explicit from the applying Bayes' congruence theorem. Okay, so we call this kind of modular forms, which comes from a character of imaginary quadratic extension having the complex multiplication. So the second application is to elliptic curve E defined over Q with conductor N. So to such elliptic curve, we can associate the Hasse-Weil L function. Okay. So at the factor at the P not dividing the conductor is 1 over something which is a quadratic in P to the minus S. And the coefficient in front of a P to the minus S is minus AP, and AP is P plus 1 minus the number of rational points of E over FP. So the reduction of E over FP. Okay. And at P dividing N is 1 over 1 minus AP, P to the minus S. So AP is 0 if you have additive reduction, and the plus minus 1 if you have multiplicative reduction, depending on the slope of tangent. So the L function of the elliptic curve is fairly well known, and we can write it as a Dirichlet series. So notice that the AN here are integers. It's coming from the integer coefficients here in the L function. Okay. So in the case that E has a complex multiplication by an order from imaginary quadratic extension K, and the Theorem showed that this Hasse-Weil L function actually is equal to the L function associated to a regular ideal class character chi of K. Okay. And it's algebraic of type K equal to 2. So here we shift by S minus that's k minus 1 will be 1/2. Okay. And as we discussed in part 1, that we know that to such chi, we have associated modular form. So which means that for this elliptic E with a CM, there is a modular form with a CM whose L function agrees with the Hasselbalch L function of the elliptic curve. Okay. And the Hasse conjecture that if we look at this Hasselbalch L function for elliptic curve, and it's a twist by ideal class characters of Q. And for the elliptic curve E without CM, okay, then this L function should behave the same way as the elliptic curves with CM. So in other words, he's saying that if we apply the converse theorem, that means that this L function associated to elliptic curve over Q is equal to L series of some new form of weight 2 and for gamma naught n. And that is precisely the Taniyama-Shimura modularity conjecture. So this is equivalent to the old Hasse conjecture. Okay. So so here we talk about given elliptic curves, okay, over Q with conductor n. Then its Hasse L function is equal to L function of a weight 2 cusp forms for gamma naught n. Okay, and as we noted before, that so this F with Fourier coefficients a n comes from the Hasselbalch L function, so they are in Z. Okay. So conversely, if we have a new form of weight 2 of level n, and well, which has a Z coefficient, and actually one can prove that there is an L function such that this LFE is equal to the Hasselbalch L function of an elliptic curve. So I expect this to be explained by the speaker who will talk about, and I think in his second talk on the modular curve. Okay. And as we have heard several times, that this Taniyama-Shimura modularity conjecture was established for the semi-stable by Wiles and the Taylor Wiles, and in general by Breuil, Conrad, Diamond, and Taylor. Okay. So this Weiss-Converse theorem gives very strong theoretical evidence on why the elliptic curves over Q should come from modular form or weight 2. Okay. So the third application is that we consider the complex representation of the Galois group over Q. So let's say degree n, continuous, irreducible, complex representation. Okay. So to such kind of a representation, Arctin has defined the Arctin L function. Okay. So basically, it's 1 over the characteristic polynomial of the Frobenius. Okay. But the Frobenius is determined up to the inertial subgroup. So we restrict the action of Frobenius on the part of the representation space, which is fixed, pointwise fixed by the inertial subgroup, so that this thing is well defined. But since inertial subgroup is trivial most of the time, so we can see that this denominator here is a polynomial in p to the minus s of degree n. Okay. So then the Arctin conjecture that if rho is a non-trivial irreducible complex representation of degree d, then it's the associate this Arctin L function, well, has the analytic behavior as we have seen before. Namely, it can be extended to the whole complex plane, holomorphic everywhere, and BVS, and satisfy the functional equation, and with some gamma factor, which he also defined before. And after we completed with the gamma factor, then the resulting function will have a symmetry between rho and the control gradient of rho and the S and the 1 minus S. Then in front of the in the functional equation, we have the exponential function which conduct the rho to the 1/2 minus S and times non-zero constant. Okay. So this Arctin conjecture, when the degree D is equal to 1, follows from the class field theory and the work of Hecke. Okay. And in general, Brouwer proved the conjecture, except that instead of a holomorphic, and he showed that it has a meromorphic continuation. So the whole issue is the holomorphicity. Okay. So we observe that when degree is at least 2, when we twist the representation by a character, okay, and we still get a degree 2 irreducible representation. So inside the Arctin conjecture, when D is greater than 2, I mean, this behavior also includes the behavior of rho tensor by characters, okay. And in particular, when we look at a case that D is equal to 2, okay, and so we take the complex conjugation in the Galois group, which has order 2. So look at the determinant of rho at a complex conjugation. Then determinant is 1 or minus 1. When it's minus 1, we say that the representation is odd. In this case, the gamma factor is 2 pi to the minus S times gamma S. Okay. And so then we can use the converse theorem to conclude that Arctin's conjecture for odd degree 2 representation, complex representations means that this L function associated to rho should equal to L function of a weight 1 newform G. Okay. So, sorry. Okay. So now here we have 2 sets of L functions. One is L functions associated to equivalence classes of degree 2 and odd complex representations of Galois group, GQ. And the other side is L function associated to weight 1 normalized newform. Okay. So to compare these 2 sets of L functions, the Linsayer showed that so any from if we have weight 1 newform, that L function is the L function of degree 2 odd Galois representation. Okay. On the other direction is that every weight degree 2 odd Galois representation L function is equal to L function of the weight 1 form, and that is the result of Carré and Berger. Okay. So as by applying the Sayre's modularity conjecture, okay, which we're going to discuss in a while. Okay. So here I would just like to mention that this Arctin's conjecture was a big motivation for Langlands to formulate the so-called Langlands program. Okay, and also in order to prove what we just said about a degree 2 odd Arctin conjecture case for the representation of degree 2 and odd. Okay. In the old days, the discussion is done in the following way. One looks at the projective image of such a representation. It could be a dihedral, or A4, or S4, or A5. If it's dihedral, we know it's coming from inducing the character of a quadratic extension, then the Arctin conjecture holds. Okay. Then if it's type A4, to prove that case, Langlands developed the so-called base change, the theory of base change, to solve that case. Then Langlands' argument was extended by Turnell to solve the S4 case. And the most difficult part is those representation of the type, which is so-called A5. And Richard Taylor and his group worked a lot on this. Okay.
Is it resolved? A5 case?
I mean, they established this for many cases, but they did not establish that completely. Okay. So now let me talk about the Galois representation associated to a new form. So we take a normalized new form or weight k, level n, and the character chi. Okay. We take a prime L. Okay. So we said before that the field of coefficients for G, well, it's a finite extension of Q. So then we just, in this field Kg, we just take any prime ideal or any place which is above L. We call that lambda. Okay. So we complete this field of coefficients at the place lambda. Okay, so it is a finite extension of QL. So the theorem is that, so to this normalized new form G, there's a two-dimensional continuously reducible L-adic representation from Galois group of Q to GL2 of with coefficients in the local field. Kg lambda, okay. And this representation is unramified outside L times n. Okay. So you can see that sometimes people call that a lambda-adic representation. So I would just call that L-adic representation, okay. So this representation at the unramified place has the following property, namely, so if I take P unramified, it's a degree 2 representation. So we compute its, though I can find that it's a trace of the Frobenius of the P is equal to AP, which is the P-Fourier coefficient of G. Okay. And the determinant of the Frobenius of the P is chi P times P to the K minus 1. Okay. So both trace and determinant, in other words, the characteristic polynomial of the Frobenius of P are independent of the choice of the L, as long as it's not equal to P, and independent of lambda above L. Okay. Another important feature is that if we look at the determinant of the representation of the complex conjugation, we find that it's -1. So in other words, such representation is odd. So this theorem is proved by different people for different weights. So it started with the work of Eichler Shimura for the weight k equal to 2. And so I think this work will be explained in the lecture this Thursday. Okay. And then Delin proved it for weight k greater than 2. And Delin Sayre did it for the weight k equal to 1. So let me just say a little bit more about this associated L-adic representation. Okay, for the weight k greater than or equal to 2, it is motivic. Okay, so that means it's coming from geometry. So first of all, representation itself, well, it's a piece of the Galois action on the hyperbolic cohomology H1 of the modular curve, okay, with coefficients in some kind of L-adic sheaf, okay. And furthermore, if we look at P, which is outside of L times N, and look at the action of the Frobenius at P. So that can be identified as the Frobenius action on a two-dimensional subspace of the middle elliptical homology of an k-1 dimensional variety over finite field Fp. Okay, so this second way of viewing that is very important. So that means that the eigenvalues of this Frobenius P, okay, satisfies the Riemann hypothesis. So namely, the two eigenvalues from the beta of Frobenius will have the same absolute value. In this case, is a p to the k-1 over 2. Okay. Okay. And when weight k is equal to 1, and the Galois representation actually has finite image, and it is identified as a complex representation, as I mentioned before. Okay. And since finite, because since has finite image, so the Frobenius T here, well, has finite order. So its eigenvalue should are the roots of unity. So they have absolute value 1, which also satisfy the same property. Okay. So now our AP being the sum of two eigenvalues. So then this tells us that has absolute value bounded by twice p to the k-1 over 2. So this is the famous Ramanujan conjecture. Okay, this is how it is proved. So for the Galois Galois representation of the Galois associated to a new form, okay. We can, that also induces degree 2 representation of the Galois group into the residue field of lambda, okay? So which is a finite extension of FL, okay? So, so this is one way to get degree 2, a nice degree 2 representations over finite field. And Sayre's modularity conjecture says that any continuous odd irreducible two-dimensional representation of GQ of the Galois group of Q over a finite field of characteristic L is isomorphic to what we have seen, to the reduction of this Elliptic Galois representation associated to some normalized new form. Okay. So the conductor of G is equal to the Arctin conjecture of the representation of rho. Okay. And Sayre gave a recipe for the minimum weight of such a G. Okay. So this conjecture was proved by Carre for the case level 1 in 2006, and then with that in the joint work with Venton Berger in 2009 for in general. Okay. So let me give two consequences of the Sayre's modularity conjecture. Okay. So the first is that we can take this representation of degree 2 representation of GQ over finite field to be coming from elliptic, from the reduction of the Tate module associated to an elliptic curve defined over Q. Okay. So in this case, then Sayre actually, when he posted that this conjecture, he already showed that his modularity conjecture will imply the Taniyama-Shimura modularity conjecture. And the second consequence is the what I talked to earlier, that the Arctin conjecture for odd degree 2 irreducible complex representations hold. Okay. So to do this, they first applied the Sayre's conjecture, means that you can pass to the residue field. It comes from modular form. And then when we need some kind of modularity lifting theorem to see that it really comes from a weight 1 form. Okay. So the next conjecture I will talk about is the Sato-Tate conjecture. So again, we have a normalized new form of weight k, level n, and a character chi. Okay. So we have seen that at primes p are not dividing n, this Fourier coefficients AP. It's a sum of two eigenvalues, alpha and beta, of the Frobenius action coming from the Elliptic representation. Okay, and alpha p and beta p have the same absolute value, and their product is chi p times p to the k minus 1. Okay. So let's assume that the chi is trivial. So then their product is equal to p to the k minus 1. That means that the alpha p and the beta p are complex conjugate of each other. Okay. So let's write this alpha p in its absolute value, p to the k minus 1 over 2 times the unit vector. Okay. Now, because that beta p is a complex conjugation of alpha, we may assume that this angle associated to alpha lies between 0 and the pi. Okay. And then our AP will be p to the k minus 1 over 2 times twice of cosine of this angle, theta p. Okay. So let me say it again. So to each, we fix this new form, normalized new form. We look at the p's Fourier coefficient, which is the eigenvalue of Hecke operator p. Okay. So we write this p to the k minus 1 over 2 times cosine theta p. So as the p varies, we have collected a family of angles, theta p. So we want to understand how do these angles, theta p, distribute in the interval between 0 and the pi, okay, as p goes to infinity. Okay. So if this form has a CM, then so I should have add here that I assume the weight is at least 2. Okay, the argument below here applies to weight at least 2. I should say it from the very beginning. Okay, so if G has a CM, then we discussed before that Theorem showed that this L function of G is L function of a character of some imaginary quadratic extension. Okay, so as such, when the prime P is inert in K, then we immediately will have AP equal to 0. So that means that AP equal to 0 for half of the primes. Okay, and then for the remaining prime P, which splits in K, let's look at this angle theta P, and that angle. Those angles are uniformly distributed on the interval from 0 to pi with respect to the measure 1 over 2 pi d theta, just the usual measure. So that it's a total volume. Its measure total value measure is 1/2 because the other 1/2 goes to the split to the inert prime P. Okay. So the distribution for the forms with the CM is clear. Okay. So then the Sato-Tate conjecture is for the normalized new form with no CM and the weight k at least 2. Okay. So in this case, the conjecture says that this angle theta p should be uniformly distributed with respect to a different measure. It's the Sato-Tate measure, 2 over pi times sine squared theta d theta on this interval. Okay. So this means that if we take any interval from alpha to beta contained in the interval from 0 to pi, and we count the number of primes p up to x, such that the angle theta p falls in this interval from alpha to beta, and compare that to the total number of primes up to x, then we let x go to infinity. This ratio is equal to the this Sato-Tate measure integrated from alpha to beta. Okay. So the Sato-Tate conjecture was initially stated for elliptic curves of Q, okay, by Sato and Tate independently. And then now, because of the modularity theorem, we know that we can also view that as coming from the new forms, two new forms with integral coefficients. But actually, these conjectures can be stated for all. Okay. So Sayre has proposed the following approach to prove the Sato-Tate conjecture. He proved that the Sato-Tate conjecture would follow if we show that the L function associated to the all the symmetric powers of this new form, which originally was defined in terms of the Euler product. So it has a natural boundary of absolute convergence. Okay, it's to the right of that vertical line. But if this L function can be extended to a function which is also holomorphic on the boundary of absolute convergence and the non-vanishing there, and for all the symmetric powers, then the Sato-Tate conjecture would follow. Okay. Now, because to this new form G, we have associated families of the L-adic Galois representation, I can also state this as L function associated to the Galois representations. Okay, we have two views. Okay, so let me just say a few words. A normalized cuspidal new form is reinterpreted by Langlands as a cuspidal automorphic irreducible representation of GL2 over Q. Okay. So then, according to Langlands' philosophy, if our modular form G has no CM and a weight at least 2, then its symmetric powers should be a cuspidal automorphic irreducible representation of GL R plus 1 over Q. So when R is equal to 1, that's our original G, that's for GL2 over Q. Okay. So if if the symmetric power is a cuspidal automorphic irreducible representation, then one knows that its L function actually is entire. So in particular, it behaves is holomorphic on the boundary of absolute convergence. Okay, and Jacques Chalaik has showed that it will be non-vanishing on the boundary. So therefore, if one knows that these symmetric powers, they are cuspidal automorphic representations for GR plus 1, then we would have for all R, at least then the Sato-Tate conjecture would follow. So this is the big picture behind the proof. Okay. So the Clozel, Harris, Schlepper, Baron, and Taylor has this big paper which proved the Sato-Tate conjecture for elliptic curves over totally real fields under a mild assumption. Okay, and then this joint work is further extended in Barnett Lam. I don't know how to pronounce it. Gerardi and Harris and Taylor in 2011. So they work on the side of Galois representations. Okay, so they did not prove that. So the if the symmetric powers are cuspidal automorphic representation, then the corresponding Galois representation is called automorphic for Okay. So they did not prove that the Galois representations GQ is automorphic, but they proved that it is potentially automorphic. That means that it's restricted to a finite index subgroup of GQ. It is automorphic. That means they correspond to the cuspidal representation of GL and R plus 1 over a higher extension of Q. Okay. And the key thing is that this potential automorphy is enough to derive the desired analytic behavior of the L function on the boundary of absolute convergence as Sayre described. Okay. Therefore, they proved the Sato-Tate conjecture this way. Okay. So in their paper, they also proved the Sato-Tate conjecture for elliptic curves over totally real fields. Okay. So very recently, Newton and Theorem proved that the symmetric power of such G, it is indeed a cuspidal automorphic representation of GLR plus 1 over Q for all the R. I should just add that this idea about potential automorphy of Galois representation, okay, from that the property to the right to the behavior of L function on the boundary of absolute convergence was used again in more recent development to prove the Sato-Tate conjecture for the elliptic curves over CM fields. There's one paper. And another big paper is that over quadratic extensions of totally real fields. Okay. So now the Sato-Tate conjecture for elliptic curves are known for quite a bit. Okay. So that ends my discussion for the what happens for the module forms for congruence subgroups. Now for the remaining time, I will talk about the module forms for non-congruence subgroups. Okay, so let me start with the elliptic curve over Q with conductor M. Okay, so we have seen one example. Okay, but this is a general situation. So the Bayes theorem tells us that this elliptic curve is isomorphic to the modular curve for finite index subgroup gamma of SO2Z. Okay. So this curve has genus 1, so it has a one-dimensional holomorphic differential FZ/dZ and on the modular curve, and we can write this FZ in its Fourier expansion. Okay. Now we assume that A1 equal to 1. Okay. And on the other hand, we also know that its Fourier coefficients are integral outside the M. Okay. On the other hand, this E is elliptic curve defined over Q. So the modularity theorem tells us that it's a Hasse-Weil function. Well, so it's comes from two new form. We call that a G with Fourier coefficients Bm. Okay. So it was shown by Arctin and Swinton-Dyer and also Cartier that we have no idea about the behavior or the Fourier coefficients of non-congruence form because there's no Hecke operator. Okay, but on the other hand, they found that if we just take the Fourier coefficients AMP, AN, and AN over P, okay, they satisfy the three-term congruence relation with coefficients, the minus BP here coming from the P's eigenvalue of the this congruence module form G, and the plus P in front of AN over P. Okay, and so it's a congruent to 0 modulo a power of P. And this powers of P increases as P divides N as a higher order. Okay. So if the curve gamma itself is congruence, then this F is equal to G then this congruence becomes equal to 0. So this is the then this is what we solved, is the recursive relation from the Hecke operator. But if it's a non-congruence, then what we see is that we have this congruence relation replacing the equality. Okay. So in general, let's assume that we have a non-congruent subgroup with dimension of weight k cusp forms that's equal to D with a dimension D. And we assume that we assume that this curve x gamma is defined over Q such that cos infinity is a Q rational point. And also we remarked before that the weight k cusp forms for gamma has a basis, which is, integral outside some integer m. Okay. So since there's no Hecke operators, so all the advancement on the non-congruence forms are guided by numerical evidence. Okay. So from computing about a handful of examples, together with what happens for the elliptic curves case we saw before, this Arctin and Swinton-Dyer in their paper suggested that there could be some kind of a congruence relation which holds in general. Okay, so that means that which is for P, which is not dividing M. Okay, this space of cusp forms should have a basis. Okay, D forms of them, such that for each form you look at Fourier coefficients. Well, it satisfies three-term congruence relation. Okay, so, and the number in front of an is some algebraic integer which has absolute value, which satisfies the Ramanujan bound, and the number in front of an over p is a root of unity times p to the k minus 1, just very much like what we saw for the Hecke three-term Hecke recursive relation, okay, except that this now is a congruence relation, okay, modulo suitable powers of P, okay. So notice that this is that we first make choice of P, then we can find a basis, and each basis element has satisfied this three-term congruence relation, okay. So in their mind, this basis Hi will play the role of the eigenforms of a ghost p-adic Hecke operator. Okay, and this basis, if it exists, usually should vary with p. Okay, so this is a very interesting proposal. Okay, so in order to explain, why there's a congruence and why this AP and the BP have the properties that's described, show did a lot of work on that. He started by attaching a Galois representation to the space of cusp forms. Okay, so now we assume that the weight is at least 2. Okay, so then show proof that so there's a compatible family of 2D dimensional chaotic Galois representations of the Galois group Q, which unramified. So if I look at the chaotic representation, then it is unramified outside of L times M. Okay, and its construction is very much like what we said for the congruence form. It's basically it's the same. Okay, similar, I should say similar. Okay, and it has the following property. Okay, so so at the unramified prime, we look at a characteristic polynomial of Frobenius. It is a degree 2D polynomial. Its coefficients are in Z, and they are independent of L. And second, so all the roots of this capitalist binomial have the same complex absolute value, namely, which is p to the k minus 1 over 2. Okay. And thirdly, this representation is motivic, just like the way I described before. And it has a Hecke weights 0 and the 1 minus k, just two different Hecke weights. Each has multiplicity d. And he further showed that so if the p is large enough, okay, and if we take form from this non-congruent subgroup of weight k, and suppose that it's this Fourier coefficients are p-adically integral, okay, then the Fourier coefficients of f satisfy a long congruence relations. So now it has 2d plus 1 terms. Okay, so started with an p to the d, then that goes down, divided by p each time, and finally with an p to the minus d. And the coefficients are exactly coming from the coefficients of the Congruence binomial. Okay. So show proof that in general, the forms for non-congruence forms satisfy long congruence relation. Okay. And we have good information about these coefficient, the C's. Okay. So if there are some operators on the space of cusp forms and also on the representation space, which can, such as the Hecke operators, if gamma is a congruence subgroup, then we can decompose the respective spaces, and then we can get the shorter congruence relations. Okay. So this is so without Hecke operator, we cannot cut, so we have long congruence relation. And if we can further cut, then we'll get shorter ones. Okay. So I would end by posing some open questions and recent developments for the non-congruence forms. To me, the most important question is the automorphy of show representations. Okay. Because these show representations are the motivic, and that they are ramified only at finite many places. So according to the Fontaine-Laser or that conjecture, so they should correspond to automorphic forms or automorphic representations of GL2D over Q. Okay, so if this happens, then we say that this show representations are automorphic. Then we say it's potentially automorphic if its restriction to a finite index subgroup is automorphic, as we saw before. Okay, so if show representations are automorphic, then this long congruence relations that we saw before gives us very interesting congruence relations between the Fourier coefficients of non-congruence forms and the Fourier coefficients of congruence form, just like what we saw for elliptic curves. Okay. So what we know about automorphy is very little. For the d equal to 1, this follows from the Sayre's modularity conjecture and also the modularity lifting theorem. Okay. So in the joint work with Arctin, Liu, and Lin Long, we proved the case d equal to 2, and the representation space admits the quaternion application. So there's extra symmetry in that. In this case, the corresponding automorphic representations is either for GL2 plus GL2 or GL2 cross GL2, and which is further can be viewed as forms for GL4. Okay. And Antonio and JKE show that when d is equal to 2 and the weight is odd, at least 3, then it is automorphic, corresponds to GL2 cross GL2. And also in the recent paper with Tony and Lin Long, we give an infinite family of potentially automorphic show representations. Okay. I just want to remark that in general, it's not easy to prove the automorphy of show on the market. Okay, because they usually assume the regularity condition, namely distinct Hodge-Tate weights. But in case of show representations, that's a case only when D is equal to 1. When D is at least 2, then they are no longer regular. But very recently, Caligari and Girardi came up with a new kind of modularity theorem, which applies to irregular Galois representations. Maybe they can be used. Okay. The second is that to which extent does the Arctin ASD congruence hold? Okay, so when D is equal to 1, and the ASD congruence is the same as show congruence, then we know that holds. Okay, and when D equals to 2, then if there's a QM on the space of cusp forms, then we also show that form that holds that. In Lin Long's talk, she gave various examples. Okay. And the show proved that if we look at a Frobenius at P, okay, if that action is diagonalizable and half of its eigenvalues are p-adic units, then the ASD congruence also holds. But in 2014, my ex-student Kibel Beck and the 2016 Kazaliki and Show, they gave examples where ASD congruences hold only for half of the primes. So one just doesn't know, well, what's a good way to describe this situation? Okay. So the third question is bounding the Fourier coefficients of non-congruence forms. Okay. So we know that if we have congruence forms, because Ramanujan conjecture holds, so the Fourier coefficients an are bounded by n to the k over 2 minus 1/2 plus epsilon for all epsilon positive. Okay, so this epsilon here is used to absorb the number of prime factors inside n. Okay, but for non-congruence forms, Selberg gave an example to show that the Ramanujan bound would fail for certain non-congruence forms. On the other hand, he also showed that the Fourier coefficients are bounded by k over 2 minus 1/5. Okay, so it's weaker than the Ramanujan bound. But that one does, well, what is the best bound? That's another open question. Okay, thank you very much. That's all I want to say.
Thank you, Professor Winnie. Let's all give her a round of applause for this wonderful exposition. Are there any questions from the audience?
How much computer programs you use?
What?
In your works or your students, do they, how much and what kind of computer programs?
My work doesn't use computer because I do not compute. But to come up with conjectures, you really have to compute examples so that you know what to conjecture.
Yeah, I mean for coming with a conjecture, you have to have some data.
You have to make it, so you need data. So.
Yeah,
So Arctin is, I mean, really super about this. So, yeah.
They use computer, I think, even in their famous paper on the non-congruence forms, 70s.
Yeah, he's expert in computing things, and
even
that's
Atkins and similar to Dyer.
Yeah, same paper, I must say.
Yeah, and to observe the phenomenon from the data, and that I think is amazing ability.
So
But on
he,
the other hand, which, as I said at the beginning, that I mean, because non-congruence forms are abundant, that means the non-congruence forms, I mean, are more general. So we, I mean, should not expect a very, I mean, rigid the relationship like for the congruence forms. So, but I think these congruence relations on the Fourier coefficients are very interesting.
Hello. Hello, Professor Lee. I
Yes.
wanted to know if for the bound for the non-congruence modular form, is the Selberg's bound is still the best bound, or how far we have gone on that?
I do not know. I do not know. So that's why that's an open question. I don't know whether minus 1/5 is the best possible.
I see. But this recent the work of Caligari on the Caligari and his collaborators on unbounded denominator conjecture, the Atkins, and Masons, is whether you know if that work has some impact already on the on just
On the
settling
size
little
of the
bit,
Fourier coefficients.
just very minor, yes, yeah.
I do not know. You may ask the speaker when he speaks.
Yes, I'm waiting. Yeah, for Vasily. Yeah.
Actually, for me, more immediate question is, say, what kind of bad prime should go into M? Because we say that, okay. So one obvious source is that the primes dividing the cusp width. Okay, just one, which is the same as the congruence forms. But there are other primes which could, I mean, there are examples where other primes which come in, which comes from the geometry. Okay. And Will Chen thinks that because he gave this modularity interpretation with a G structure for the modular curve attached to gamma. So he thinks maybe the order of the primes dividing the order of G should also be bad. I don't know. So
yeah, okay. Yeah.
So when has unbounded denominator and to estimate the size, I think becomes tricky, isn't it?
That's true, like, yeah. And that's what probably the Selberg's idea to understand, like to work with the vector valued modular forms, to study better the non-congruence modular form, maybe like most of the time for any representation, kernel of rho might be the non-congruence subgroup, and to hope that, so what you mentioned about the geometrically, probably the geometry is coming with these representations.
I hope these representations, I mean, can come to play, because for congruence forms, they play vital roles. So, yeah.
Yeah. Yeah. Thanks a lot.
Thank you.
Any other questions or comments?
Yeah, ma'am, I have one question. Is it interesting to see, because you talked about potential automorphy. From potential automorphy to automorphy, means suppose we have a cyclic base sense from Q to cyclic extension of Q restricted to Z K. K is a cyclic extension of Q. If we have some potential automorphy results there, see, is this interesting to see? Can we have a descent to Q?
Yes, I mean, certainly, I mean, first I would remark that in one sense, potential automorphy is easier because we have a representation of a large group GQ. When we restrict it to a smaller group, sometimes they decompose. so into smaller pieces. So then it's a higher chance that the smaller pieces, each has lower degree, they are each piece is automorphic. So then the question is that if it's automorphic on the smaller group where the original, so they can be extended to automorphic of a larger group. So yeah, that's the hard question. But I find that just to use potential automorphy and then to get the information on the L function is very clever, and to prove the Sato-Tate conjecture.
Yeah, in proving modularity problems, means people compare two representations, equivalence of two representations. Means, so what we have means, if we have a two-dimensional representation, if we want to compare, then we have faulting Sayre method, some Sayre's method.
Yeah.
Means in comparing. So if we have some higher dimensional representation, means is there some way to compare two representations? Just like Sayre's method, Sayre's generalization of interpretation of.
Yeah, I'm not aware of that. Yeah, as you said, we don't. Yeah, it's a degree 2, which is the best known. Yeah. And also in the old days, the modularity lifting is also restricted to degree 2 representations. Yeah.
Okay.
Yes.
Any further questions? If not, let's thank Professor Lee for the 2 very nice talks that we had from her.
Thank you.
And over to the organizers.
Thanks, Professor Winnie, for these talks, and thanks, Siddhi, for chairing it. Maybe we will see you again in Pune. You have, I think, given 2 talks 2 times in Pune itself, right? Luca, you can stop the recordings maybe and streaming.
Okay.